Hi,
Hi, how are you?
I got a new camera.
Oh, good. Yeah, looks good. Looks good.
How am I? Well, I've been fighting with a computer program,
Oh,
and Dick really wants to know about some authors. I did send you a list of
yeah.
them.
Yeah, I got the list. I'm trying to
Oh,
get in touch with them. I'm going to go through the list and
oh,
email
okay.
people. But,
All right.
yeah, I don't know. I have no guarantee if anyone will respond. That's what I'm trying to find out.
Oh, okay.
Yeah.
Yeah, because they're getting antsy, and it's just
Yeah, I know.
nice.
I don't, yeah.
I
Well,
have to have some way of. Well, I don't know. I sent you the people that I noticed from the APS physics meeting.
okay. That's good. Yeah.
Yeah, and so they were already selected as being good, so
Okay, yeah, that's good. Thank you. Hello,
yeah.
Gopinath. How are you? Okay.
Well, hi.
Hi, he's good. Um, That's good. So I know that Karan is wanting to present on some things that he's been doing. He's been doing some things at the Axolotl, and I don't know when he's going to show up. Maybe in a little bit, but he wants to present on that. It looks really good. He showed me some of his proposal, and it's pretty decent.
Yeah, I know I need to get busy and put peppercorn or seeds in my microscope just behind me there. I just need to do it. I've been kind of time pressured a bit.
Right, right, yeah.
Um,
Yeah, that's always the case, isn't it?
yeah. Anyway, so
All
I'll
right.
get it done by next week. I'll try to put it together and put some seeds in the new microscope. I think it'll be more stable
Okay.
than the other one, just easier to work with. So, yeah.
Yeah. Okay. Um, well, welcome to the meeting. I guess people will be coming in momentarily, hopefully. Why don't I start in on some of the things I have? Did you have anything, Susan, you wanted to talk about or present?
No, not unless somebody knows the physical properties of microtubules and microfilaments and intermediate filaments. And by that I mean, you know the Poisson's ratio and their density?
No.
No. I don't know if anybody does. Well, they figured out Poisson's ratio for microfilaments.
Okay.
Yeah.
All right.
I'm just going to say microtubules are basically incompressible, although I know they can be compressed, but I'm just going to say that they're not. That's what Poisson's ratio is when you pull on it, how thin does it become? Because if you pull on a blob of silly putty or something, it it thins when you
Right.
pull on it. And I'm going to assume microtubules, that doesn't happen to them very often. It's not something, they're kind of a more rigid structure. But they've discovered that microfilaments change their ratio due to frequency.
Okay.
So if it's at 10 hertz, they're, they say there's 0.66 Poisson's ratio, which doesn't make any sense to me because the limit is supposed to be 0.5.
Right.
So I'm not sure where that lies, but as a standard of materials is a Poisson's ratio of 0.33. So, but that's at 10 hertz. But at 0 hertz, it's 0.5. So it's like
Yeah.
I don't know what to say. So anyway, that's been one of my problems this weekend.
Oh, it's interesting. Yeah. I'm not sure. Yeah, I don't know too much about it, but
Yeah, well, I have a paper that describes Poisson's ratio for microfilaments. It's quite thick.
Okay.
Anyway,
Hello.
that's enough of that.
Yeah. Hello, Harini. How are you?
Hello,
Hi.
I'm good.
Good. Welcome to the meeting. So, why don't we get started on some things? First of all, I know some of you are here for Google Summer of Code. Those proposals are due on the 19th. And so that's coming up sooner than you'd think. Some of you are going to be, well, there are two projects. We have the microsphere project with axolotl embryos, and then we have the graph neural networks with graph neural networks, I guess. And some of you have asked me about data for that. The data I've been trying to, I've sent you some links to what we call the DevoZoo, which is a site where we have different types of data. I've also pinned some things, if you're in the Slack, pinned some things up on the Slack channel. So that's, if you want to know more about the deadlines and the format, go to that. And then we also have, if you want to send me a rough draft of your proposal, then, by all means, please do. I'll review it. And I have in the pinned content on the channel, on the DevoWorm channel, I have sort of a drawing of what it should look like. You'll see basically an outline, the three components of it, and especially the schedule. And in some communicating with INCF, I found out that the schedule for both projects will be half time, and it's 10 weeks. So if you schedule out 10 weeks of coding time and maybe 2 or 3 weeks of community time, I think at the beginning there's a 2 or 3 week period of community activity, and then there's this 10-week period of coding. And keep in mind that that's about a half time, so that's about 20 hours a week. So when you're saying you're going to do something in a week, that's 20 hours, and then that's it. And so, I think you can extend it out past 10 weeks. There's an extended, there's some flexibility in the scheduling, but I don't know. It'd have to be, we'd have to talk about that because I'm not sure. I think it can go out to 20 weeks, but you would have to distribute your work accordingly. So, this is, I think INCF has decided on some rules for this. So I wasn't a part of that decision-making process, but it's basically the 10-week period, and then you can extend it if you want to take it slower. But that's for this project, it's half-time. Some of the projects, and not in our group, are different than that, but that's what we're going to go with. So, yeah. So, Richard Gordon asked, what data do you have for axolotl embryos? And I think it's that data set that the initial data set Susan had. I don't think we have anything newer right now.
I have a bunch of data that I put on my Google Drive.
Okay. Yeah. I don't know if that's, yeah.
There's quite a bit of it. Like I said, I'm going to get more data this week. I will work on it and make sure I get 3D images of a seed of some sort.
Okay. That sounds good.
Yeah.
And I'll figure out a way to distribute it. It's tricky because you have to have I'll figure out something. Okay.
All the images will be of a lower megapixel value than the ones for the flipping microscope because the cameras are only a 1.3 megapixel on my little microscopes. So they'll be smaller, so you can email them around.
Okay. Oh, that, yeah, I guess that would be, they're not as large, the files, so it should be good. So, I mean, that's kind of our limitation, is when the files are really big, and we have a lot of them and they're really big. Yeah. Oh, he used images from the research paper for montaging. That's Harikrishna.
Okay, I have a bunch of other ones. Of the axolotl embryo taken with the flipping microscope. And then I'm going to end up with some bunch of seeds from the stationary ball microscope.
All right. And Richard Gordon said, can we see the results? I don't know if that's... oh, okay, that's Harikrishna. Actually, it's the same thing I had shown before. So that's... yeah. Okay. Well, yeah, as we make progress on this, and we'll try to facilitate the transfer of data, make sure that we know. So it seems like there's a flipping microscope data set and a ball microscope data set. Is that correct?
Yes, the ball microscope data is not of an egg because, like I said, we've been having issues with those salamanders not laying eggs all winter. I'm not sure what's up with that, but the water was bad this summer here because it was so dry, so they were not as well a salamander as they should have been. Like, all of mine are kind of limp.
Oh.
Like, you pick them out of the water and usually they fight because they don't like it, and they just lay there limp. So
Wow.
the poor things are still recovering. Like,
Moody axolotls, I guess.
yeah.
Okay. Well, that's good. I think, yeah. So we'll keep moving on that. Might as well. Yeah. I don't know if we have anything else people want to share. I know Karan may be coming. We'll see. Okay. Let me share my screen here. So one of the things I've been doing is going through some of these things with graph neural networks. And I don't know who's interested in that project here, but I've been collecting some resources on graph neural networks and some of the things people have been doing on this. So this is a pretty exciting area. It's very fast moving, so it's kind of hard to maybe wrap your head around what's going on in the area. So this is, I've got 4 things here and then like 3 preprints I'll show. So this one is talks about higher order GNN suffer from the KWL and network complexity. So this is where you have it's actually N star star K complexity, but this is their notation for a network and its complexity. And it's a problem in graphs. It's just that you have a lot of nodes and a lot of connections. Here we introduce a new graph isomorphism heuristic and corresponding equivariant neural networks that offer more fine-grained control over the trade-off between scalability and expressivity. And so this is an image here of their workflow. This shows the power of the proposed algorithms and neural architectures. So they use something called SpecNet, and they plug it into this LWL, and it gets processed out to this WL. And so this is let's see if I can find the paper here. So this is 13139. This one here. So this is SpecNet, sparsity aware permutation equivariant graph networks. So this has to do with message passing and message passing graph neural networks. They have clear limitations in approximating permutation equivariant functions over graphs of general relational data. More expressive higher order graph neural networks do not scale to large graphs. They either operate on k-order tensors or consider all k-node subgraphs, which means they basically consider a lot of different nodes and a lot of different connections, implying an exponential dependence on k and memory requirements, and do not adapt to the sparsity of the graph. So they have this dependence on the number of connections. So I've talked about hairball networks. Hairball networks are very dense with respect to k, and there are a lot of connections. So it's considering all subgraphs with all these nodes k, and it's just doing a lot of things at once, and so that's going to tax the memory requirements. So this doesn't adapt to the sparsity of the graph. By introducing new heuristics for the graph isomorphism problem, and this is a problem in graph theory, and they talk about it in the paper, we devise a class of universal permutation equivariant graph networks, which, unlike previous architectures, offer a fine-grained control between expressivity and scalability, and adapt to the sparsity of the graph. These architectures lead to vastly reduced computation times compared to standard higher-order graph networks in the supervised node and graph level classification and regression regime, while significantly improving standard graph neural network and graph kernel architectures in terms of predictive performance. So they kind of go through in this paper sort of how people are using it. So in recent years, numerous approaches have been proposed for machine learning with graphs, most notably approaches based on graph kernels, and there's some citations here, or using graph neural networks. Here are graph kernels based on the one-dimensional Weisfeiler-Lehmann algorithm, 1WL, a simple heuristic for the graph isomorphism problem, and corresponding GNNs, have recently advanced a state-of-the-art in supervised node and graph level learning. However, the 1WL operates via simple neighborhood aggregation, and the purely local nature of the related approaches misses important patterns in the given data. So they kind of go through, like they use this algorithm as a KWL as a basis, and they're treating it as sort of a problem that they want to improve upon. And then, so a more powerful algorithm for graph isomorphism testing is the k-dimensional algorithm. This algorithm captures more global higher-order patterns by iterative computing, a coloring, or labeling for k-tuples. So they do this coloring. There's a problem in graph theory called the n-color problem, where it's multiple colors. The idea being that you have different nodes that are different colors, and you want to keep them separate. So it's a problem of sorting the network and making sure that the colors are different in different places. And so, this is a highly computationally intensive. And so they have more survey here. However, since the algorithm considers all n sub k, many k-tuples on an n-node graph, it does not scale to large real-world graphs. So these computational methods, sometimes they don't scale very well. So new neural architectures that possess the same power in terms of separating non-isomorphic graphs suffer from the same drawbacks. Their memory requirement is lower bounded for n sub k for an n-node graph, and they have to resort to dense matrix multiplications. But there are ways around that, and they describe it here. And so then they describe the present work, so they work on this problem of this graph isomorphism problem, and they denote it this way, and then they kind of work this through. And then they introduce this method called SpecNets, which actually tackles this problem. So that's one area that... hi, Karan, how are you? Okay. The next one here is on topological graph neural networks. This is an ICLR paper from this year. So basically, TOGL, a layer that makes GNNs topology aware, topology plus GNNs. We are motivated by a simple observation. GNNs cannot easily capture certain topological characteristics of a graph, such as its number of cycles. So the GNNs that we think about, the conventional GNNs, they have a problem capturing some of these higher order graph theoretic properties. And this is true of this first paper as well. So this shows kind of some of this, some of the performance metrics here for these different techniques. To capture topological characteristics of a graph, we use persistent homology, a method from topological data analysis. So I think we've talked about topological data analysis before, and it's basically taking things that have a shape or have some geometry and using techniques to decompose those shapes and to measure them. So you create a measurement scheme on those shapes and you measure their properties, their shape, their size, their deformation. And so this is something, they use a lot of tools from higher math, like persistent homology. At its core, TOGL learns multiple filtrations or orderings of a graph. And so this is what they do here. They have these different filtrations, which are just ways that you can order the graph. And here's an overview of how that looks in practice. The cool thing is that our topology-aware representations are compatible with downstream layers, making this layer a plug-in replacement compatible with many architectures. Our layer really shines when analyzing data sets for which topology is critical. To assess this, we replaced existing node features with random features, thus preventing information leakage. So they can actually look at things that have an actual topology instead of looking at, say, like a graph that's just built from something and you put it into like the language of pairwise connections. You're actually measuring maybe something like the surface of an embryo, where you have like points that you're using as nodes, and then you're making connections, but those connections are maybe curved in some way. So that's a topologically relevant network. And so this approach actually is tailor-made for that. And last but not least, we also show that TOGL improves a graph neural network expressivity, resulting in an architecture strictly more expressive than WL1, which we talked about in the last item. And then this is something by a bunch of people in topology, so that's great. Code is available here. This is the Borgward lab in their TOGL, Topological Graph Neural Networks package. This is on GitHub. And then that link is, I have all of this in the Slack. So you can search for the links and everything in the Slack. I just grabbed this out of the Slack so we could go over it in the meeting. So they have a GitHub repository, and the paper it's one of these two. This one, good. So this is Topological Graph Neural Networks, and this shows the same things here. They kind of show this graph, which is an overview of TOGL. So it kind of shows you have the node attributes here, you have a node map, you have K-views of graph G, you have these filtrations, which are the different orderings, you have the persistence diagrams, and then you have aggregation, and then finally output. So all these things are different operations on the data. You figure out what the nodes are, you make a node map, you have different views of graph G, then you make different orderings of it based on those views. The persistence diagrams are linking it to the topology, then the aggregation, then the output. So it's a pretty involved process, but you can link it directly to objects and their shape and their topology. The last two here are, this is another paper. Graph neural networks are still the first choice for graph data, but let's see, how do you pronounce this? Graphemers. Okay, but graphemers are coming for you. Graphemer, transformation for large graph data sets. And this is the last paper. And so this is a nice graphic of what this is. So this is the graphemer. So it's basically three components. A graphemer is a pure transformer, which is a type of machine learning tool. And this is something that has come up in recent years as a common technique for machine learning. So it's a transformer. It transforms your data. I'm not going to get into exactly the technical details, but that's what they call it. If you're this deep into neural networks and things like that, you know what that is. Plus spatial encoding, so you're encoding things in space. Plus centrality encoding, plus edge encoding. So basically what you're doing is you're taking information about the spatial location of objects or nodes. You're encoding, and then you're encoding two properties of the graph. You're encoding the centrality of the graph, which means you're finding the central point. There are different statistics you can use to approximate centrality in a graph. And it's just basically what's the centermost node in the graph. Where is the center of gravity in that network or in that graph? And so there are different measures you can use to calculate that. Then you have edge encoding. So the edge encoding are the edges here, and they have different properties, and you encode those. So you're encoding spatial information, sort of, I wouldn't say topological information, but definitely like information about the structure of the graph, and then the edge encoding, or where the edges go and where they come from. And then that's added to a pure transformer, which is then this graph former. So you're basically taking a graph, you're putting it into this machine learning algorithm, you're taking different attributes of the graph, and you're able to get this answer, this sort of thing. So no graph transformer works on large graphs, not a large data set of graphs. Scaling the transformer architecture to huge nodes or to large graphs is still an open question. So these graph formers work for moderate-sized graphs. For very large graphs, they don't necessarily work very well. I think for any developmental application, these would work fine. But I don't know if they have a GitHub repository. Let me check the paper. So this is the benchmarking graph former on large-scale molecular modeling data sets. So they're actually using the graph former on molecular data sets. And so this is the architecture here, and they're adapting it to 3D molecular dynamic simulations. So these are like things like protein folding and things like that. With these simple modifications, graph former could attain better results on large-scale molecular modeling data sets than the vanilla one. And the performance gain could consistently be obtained on 2 and 3D molecular graph modeling tasks. In addition, we show that with a global receptive field and an adaptive aggregation strategy, graph former is more powerful than the classic message parsing based GNNs. So this is like the message passing ones we talked about in the first one, but this is that's the classic sort of technique where you have messages moving from one node to another. This is a little bit different than that. And so this kind of goes through some of the stuff on. This is a quantum chemistry data set they used. This was used in KDD Cup 2021, which is a machine learning competition. In the meanwhile, it greatly outperforms the competitors in the recent Open Catalyst Challenge, which is a competition to track on NeurIPS 2021 workshop. So this is something that they had at NeurIPS 2021 Open Catalyst Challenge. It aims to model the catalyst adsorbate reaction system with advanced AI models. So this is their link here. This is something I think out of Microsoft Research. So it's at the end of the abstract here. And so they kind of go through some of the ways that they've used this technique on some data sets, a lot of molecular data sets. So it's a little bit removed from what we're doing, but they do go through some of the benchmarks that they're using here. And then finally, this is something called BrainGB, benchmark for brain network analysis of graph neural networks. So again, this is a little bit away from what we're doing, but they do these brain networks where they extract networks from brain imaging data. And so these are complex networks that are based on, different locations in the brain. They could be cells, it could be voxels, which are imaging properties. And they try to make these connections using a covariance matrix or some other type of approach. And so they're using graph neural networks to sort of solve some of these networks in a way. So this package that they have, and they don't have a paper, but it modularizes the design space. and recommends a set of recipes for effective GNNs on brain networks. So this is yet another application domain. So I wanted to go over that because I know we talk about graph neural networks. I wanted to give some examples of things in the literature. It's kind of a tough read. I know there's a lot of innovation and a lot of tough reading in there, but hopefully, maybe someone will apply and they'll have they'll have simplified it a bit, or maybe come up with a really nice example of how to do this in developmental biology. But in any case, I think Karan had a thing that he wanted to share with us. We were talking about it earlier.
Hello. Hi, Bradley.
Hi.
Just give me 1 second.
Okay.
I'm just setting the presentation here.
Okay. In the meantime, did we have any questions about anything?
Just briefly to Dick, Bradley and I are trying to find some authors for you, or for the cells papers.
Yes.
I got a whole list from the APS Physics Conference, so anyways.
It's still a matter of contacting, getting positive responses from people, or some sort of response.
Good morning.
Hi.
Right. The best approach I found to this is to make a list of suggested authors with suggested topics, and then find somebody, see if this one you specify doesn't want to do it, find somebody else.
Yeah.
That gets things moving rather than waiting for people to make up their minds.
Yeah. I'll put that into the the emails that we're gonna send out here. Yeah.
Yeah. In other words, what you want is something like a table of contents that's approximately what you would like to see in the final result, but everybody knows that the final result will be different.
Yeah. Okay.
So Susan, I think the good thing to do is select the best ones you've got there, assign a topic to each one, and don't worry about whether you get a response right away. Just make a tentative, a desired table of contents.
Yeah, okay, well, I've already introduced the one author who I thought was great 2 weeks ago. So for her, she has a whole group, so they could be any one of the people in her group that do this.
Yeah, just put her name down and a tentative title.
Okay.
Okay.
And that way Bradley can start to put together a table, propose to the table of contents.
Okay, well, I'll try to do that with some on my list there, because there were a number that were good.
Yeah.
Because the people at the journal are wondering what's going on.
We're trying.
I know, but if you wait for answers, it'll be a long time.
Yeah.
Okay.
All right.
Okay.
All right.
Hi, Bradley.
Yeah.
Should I start? I
can see your screen. Yeah. So what do we?
I was kind of going through like a few papers based on how to reconstruct a 3D model and what are the state of the art current techniques that are being used today. So the thing is, especially with the Axolotl image data set, some of the key factors, as to why we can't really apply the current methods is like, I'll just go over them, one by one. The closest, like a proper working solution for our model could be used by, something like a differentiable volumetric rendering solution to this. This is like a good GitHub project, that explains how they have a neural net that trains on spatial information of existing models, and tries to. It starts off with a very basic a very basic 3D model, and then it subtracts or has like a probability density um, function that defines how it has to generate its own point cloud and get to the final rendition of that particular model. So based on some of these ideas only, the key thing that I got from that was that there has to be some way of getting some sort of spatial information out of these images itself, because we don't have anything like depth maps, like there are things called like 2.5D images are currently uh, the most basic 2.5D depth maps. Like depth maps are very important because they actually give you the spatial information of that particular image. Like if you have a scene, so you have this sort of a spatial depth map, of grayscale pixels, and each pixel intensity actually telling you how far or close that object is relative to the camera position. So instead of relying on something like that, where is the presentation? Yeah. So what I'm trying to do here is I'm trying to first get the outlines, because this structure is like it's like an irregular ellipsoid. So the first basic inference that we can get from it is from the, at least like if we have like set of 8 sample like axolotl embryos, like the perspective of that particular axolotl embryo has been shot from like 5 different perspectives. So the first key thing is we can take information from the outlines of those axolotl embryos. So this is the first step. Like we have a raw image here, and I'm trying to mask out the there was another problem that was that I was facing when I was trying to implement current state-of-the-art 3D techniques, was that this thing has a static blue background, because the column, the images and the pixels intensity stays similar across all these sets of images. So it's very difficult to for that program at least, because they are trained on like scenes of, let's say, a video feed from a drone, or scenes from a car that's trying to make a point cloud of its own surroundings. So taking the outline after getting like a decent outline, because I was facing some issues with white like the right side of the embryos, like some embryo pixels. I think this is the dorsal side of the axolotl embryo, so it has some crossing issues. Like this part here, when you're trying to mask the pixels and trying to eliminate the blue hue background here. So I was facing some issues for that. I had to create some particular workaround, because this right side is there in almost all embryos. Coming down to the main idea behind generating the project model is, after we get the outlines of the embryo, we have to find out like 2-3 things. One of them is the axis of rotation and the degree of freedom, because these embryos are rotating, in the, like, you'll have to check for, some sort of a corresponding point, like similar points across these images, and how much they've moved across the image, to get a vague idea as to where the axis of rotation is, and the idea behind getting the displacement. Like I have a good diagram here that I could illustrate it with. So let's say this is the first perspective image of the irregular ellipsoid that we are capturing. So after that, if like for the at least stage 4 axolotl embryos that I was dealing with, that I mostly dealt with for getting at my current rendition of the 3D model, they have a very, it's mostly the degree of freedom is I think one-sided only, because there's only one axis of rotation that is there. In case we have embryo images that rotate in both ways, we'll have to maybe find out a way to find the diagonal axis of rotation, because it's rotating in the xy plane also and the xz plane also. So one key thing that we can take from this idea is that, let's say if I take a picture from this place and I rotate it maybe 15 degrees and then take a picture, So the point and the displacement of these points can be generalized to, you know, to find out how much or what exactly is the angle of our rotation. Like if I move it more than 15 degrees, let's say 30 degrees. So based on how much displacement we see of the corresponding points within the two, images, based on that, we'll be able to get our angle of rotation, which is also very important because, when we're plotting our outlines across the, along the axis of rotation, we have to specify at which angle, we want to place them. So what we have for working with a 3D model is, like I think most of the samples have 8 embryo images per model. So we have like 8 model outlines per axolotl embryo model. So 8 samples of embryo images. Then we get like 8 outlines from them, and then we have to, map those outlines across along the axis of rotation. And we can, again, there are like 2 things that we can do after that. One is like after we've mapped the outlines, we can generate a point cloud and then generate our ellipsoidal mesh, and then come at the, and then project our image onto it. Like for image projection, there's like a straightforward way of taking a normal perspective image, converting it into an equilateral projection or a Panini projection. There are various projections, Mercator projections are there. There are various ways of getting a perspective image from the main model, 3D model, or the snapshots that we've taken of the embryo. So after generating the 3D model, what we have to do is we have to project it to the image. So this was obviously, I just tried projecting it onto a very basic spherical image. Then something after that was, again, you can see, this is, I think, for 2 embryo outlines. I think it was this embryo, this is the outline, and another outline, and I took a generalized 3D point cloud and subtracted it to the particular outline, and then I projected the image onto it. This model still requires a lot more changes that have to be done based on the axis of rotation and degree of freedom part, because I'm still trying to figure out how to, like this, for this the angle of rotation is very less, like it's 5 degrees, 10 degrees along the axis of rotation. So it's easier to find out corresponding points between that pair of 2 images. Okay, wait. So Axolotl 4, yeah. I think 3, 5. Yeah. So I think it was these 2 images, these 2 images, yeah. So as you can see, the finding corresponding points is easier if they're like short at very, like with a very less angle of rotation. It's easier to find corresponding points. For very large angle of, for more like slightly more angle of rotation, I'm still trying to test getting like a more accurate way of getting the axis of rotation and the degree of freedom. But so far, I think this is actually, the thing is, when it comes to dealing with ellipsoids, and their snapshots taken with a very static background, most of these solutions really require some sort of extra spatial information that is there. So obviously, the image that we'll be getting, or the 3D model that we'll be getting, will not be like 100% accurate, but depending on the number of images that we have, like let's say if we have 8 axolotl images per sample, we'll have 8 outlines or 8 point cloud contours, that we can map onto the model, and then based on that we can improve, keep on improving. If we have like let's say 10 sets of pictures, 15 sets of pictures, so it will always be better. It will keep on improving based on the number of contours that are there, because it's like approximating the actual model from all sorts of data points that we can gather. So our main way of gathering the spatial information is from the outline itself. So increasingly number of perspectives and the way in which we can get more images would help in this manner. I did actually I just had like 2-3 hours, so this presentation just has some images, not much to show.
Oh, that's great. Yeah.
Okay, I assure you, I'm working on getting 10 images, and they're at fixed angles.
Okay. Fixed angles, so then I don't even have to find out the angle of rotation then, because it's like finding like for axis of rotation, at least for this model, I drew it like a brute force solution. I tried to find the extreme points of this and this, and found out like the centroid and found out like the line close to that centroid, and then I just assumed that as the axis of rotation. So if because it's obviously it might not work for like if the actual axis of rotation was like along this line or along this line. So getting the proper axis of rotation part could be done if I solve the corresponding points problem, and how how we can check for the displacement, like have a general like, solid equation, because if we have an extreme point here, an extreme point here, and an extreme point here, and these are the two images that we have, one from this perspective and one from this perspective. So just by checking the displacement, we can get the angular rotation. So this was the key thing that I was looking into as to how to get an accurate angular rotation after finding out the axis of rotation.
Okay,
But
well,
if there are fixed angles, so I think
they're fixed
that
angles
would
are
be really
not necessarily the same angle, because it's,
because
yeah, I'm
this
just
angle,
aiming at the egg or the seed or whatever I've got in the middle, and so the angles will be slightly different, but at least
yeah, because it's suspended in that medium, right? So okay, so because it can move and rotate freely in that medium, I think that's why
yeah,
I have to really look into.
yeah, this was it's hard to tell the angles with the flipping microscope, because it's how the embryo uprights itself is to the angles of the pictures, and that probably varies from egg to egg slightly.
Okay.
Natural variation. Anyways, I'm going to work on it this week. I've got all the pieces now. I just need to put it together properly and get you some peppercorn images and maybe some canola seed images. I have some canola seeds, so I can do that.
Okay.
All right.
So yeah, I mean, the major problem here right now is just the finding that axis of rotation and the angular rotation. I'm just using approximation right now. So I'll try different methods and see if I can get a better method to get that approximate accuracy. So far it does, I think, come to like very close approximation of that image.
Yeah, well, what you've done so far is really neat, and I'm happy to see it. I just, but I do have the newer microscope, so I can get you a proper angle of rotation. I've got a top and bottom one, and then I've got the ones that come in from the sides and the bottom, like that from all sides. So there are 10 positions.
Looks like Richard had a question about, or he had a comment. He said, look at the literature on imaging rotating asteroids. And I thought, yeah, immediately when I saw that, it was like looking asteroids. So I don't know what the...
They did also like
Yeah.
irregular shapes.
I don't know.
I can't hear you, Richard. You're muted.
He's muted.
Muted. Yeah.
As people are getting close-ups of asteroids, and asteroids usually rotate. So there should be lots of data available if you can find it.
Yeah. I'll look into that.
And they're lumpy.
That's right.
Yeah.
Okay.
The main difference from your
Very,
pictures
very
is-
regular.
Yeah, they're irregular, they have craters, which the embryo should not have.
Otherwise, a similar thing was, there was this beta project that I was going through that had lots of satellite imagery data, and they had tried to, map the actual surface reconstruction of the Earth or some other planet as well. The thing was that they were relying heavily on the, orbit coordinates and, other data, that from which they can, extract facial information. So this was kind of there, but the first thing here is, getting the embryo image itself. So that has to be went with.
That's a tough problem.
Yeah.
I just think you've done a really great job tackling this so far.
Thanks. I definitely look more into getting the accurate, axis rotation rather than the approximate rotation.
Yeah, well, with it fixed, that should help you.
Yeah, it should definitely help with the approximation part at least, because then I'll have fixed angles, as the upper and lower bounds for what the actual angular rotation can be. And then, have another thing that I was thinking as like a continuation of this project is if after generating, these axolotl embryos, I had another doubt. Can we get like a video feed of the embryo rotating? Or is it limited because of the shutter speed of the camera or something?
That's what the flipping microscope did.
Yeah, that's the flipping microscope. It was dependent on how fast that camera could take pictures. And that's how fast it could take pictures. It had a mirror on it that flipped. If you got one of the newer ones without the mirror, you probably take images faster.
Okay.
So that's an improvement that could be for the flipping microscope.
Okay. Each rendition or an extra sample per embryo data set, would have like an extra outline that would be like a closer approximation to the actual 3D model. So yeah, any data is helpful. Yeah.
In your
See what you think of the seed pictures.
One thing you could do is try to segment the embryos in a given the cells in a given image.
Okay.
Especially if you got better ones with more cells. And then try to match the cells between different images.
Okay, yeah, that's the corresponding point problem, which like taking a pair of images, finding out the corresponding points,
right,
and then mapping the displacement. So that was again a technique that I've tried for getting access.
In the time between images, the cells will not have moved very much. So, so it might be possible to do that.
Thank you, Harikrishna, for attending. When you mentioned in your talk about the 2.5 dimensions, and so this is interesting because there is this issue of like fractal dimensions. And
I don't think it's not fractal. It's just that you don't really have the dimension accurately.
Right, but like it's kind of interesting how that But I mean, so you're basically approximating a third dimension from 2 dimensions.
Right.
I don't have anything else for that.
That's difficult.
Yeah, it is. Yeah.
Especially on an embryo, because shading does not reflect the depth.
Yeah.
The blurred pixels kind of do, because you've got a depth of field, so the blurred they are, the deeper, the further away from the focal point it is. So I guess one can look at it that way.
Well, you get fancy and vibrate your microscope to get different depths.
Oh, wow. Oh, well, that would give us good blurred images, probably.
Maybe like LiDAR sensors, like state of the art. Self-driving cars have all these sorts of various sensors.
Yeah, get a really fast
Some sort of
camera.
radar.
Really fast camera. Yeah, calculate the difference in the time between light hitting the front of the embryo and the edge.
There we go.
You can use time-dependent imaging.
Oh, no.
I don't think you'll find electronics fast enough.
Not yet, no.
So if you had infinite images from infinite like perspectives, you could theoretically just say it's a three-dimensional image.
Yeah.
Yeah.
Yeah, there is a standard technique which, well, you can find out where to get it, where you take through focus images and produce a sharp image of the whole surface.
Yeah, I ran across somebody who wanted to sell me a $10,000 US a microscope, and I needed 2 of them. And I thought, yeah, well, Red River College spring for that.
Okay.
No.
Marianne Tiffany has this on with her microscope. She works on diatoms, and I'm sure she didn't pay $10,000 for it.
Oh, really?
Yes, it's just a software package. You focus at different depths. You get a bunch of flat pictures, and then it picks out the sharpest part of each picture and makes a montage of it.
Oh, okay. It's a software package.
Yeah, it's a software package, and I expect it's pretty cheap.
Okay. I would sure like to know the name of that.
Okay, send me a reminder, and I'll send you Marianne's email.
Okay.
Okay. That should, yeah.
Software for in focus. Okay.
Yeah. Well, it's very good, Karan. Thank you. Yeah. Okay. Let's see. We're at the top of the hour, so I'll probably go through maybe one more thing before we go. Do we have anything to mention before that, or?
I could bring 2-3 papers related to that differentiable, volumetric rendering part.
Yeah, let's
I
see.
think I'd have to prepare more for it.
Yeah.
Let's see.
Okay, Susan, I put Marianne Tiffany's email in the chat.
Okay, thank you.
Marianne Tiffany is an interesting lady. I think she got her PhD at around 55. She's now retired, and she used to be one of the best takers of SEMs, skinny electron micrographs of diatoms. She now uses light microscope because she doesn't have access to one-ounce machines. And so she's been doing a lot with through focus imaging to make very good pictures of diatoms, which are hard to get in focus sometimes. So she does it through focus stacking and sharpens them up.
Yeah.
So now I just need to add to the ball microscope so I can do through focus imaging.
Yeah, a linear motor on each.
On each
Yeah.
of the 10 microscopes. Right.
That should cost you 10,000.
Yeah, then yes. Maybe. Unless you have a simple method of doing that.
Piezoelectric vibrator.
I could do, a piezo movement on each one.
Yeah, possibly. At any rate, find out from her where she got the software.
Sure.
Because I'm sure she didn't write it herself.
Oh, okay.
Okay.
Were you going to share your screen, Karan?
Yeah.
Okay.
Oh, there. Yeah.
There we go.
Yeah. So this is like the next level, if we can get like, if let's say if we had a 3D data set of axolotls already there, so we could try maybe a method of this sort. There are three different metrics. Zoom in. Yeah. So 2D supervision, 2.5D supervision, and 3D supervision. There are like different, people have trained neural nets on different classes of objects. Like, they'll have a class object of an airplane. This has, I think, like 13 class objects. So they have like existing models, existing spatial information for a 3D supervision data set. For a 2.5D, I think they'll probably have depth maps and the image itself. For 2D supervision, they have like a very uh, general image data set and some pre-trained model, which has been trained on that thing. So they're trying to like extract complete information. Like, when like as humans, they're trying to use the idea that if we can, if we see, let's say, a cup right there, in front of our table, we can, imagine or generate the spatial information and understand that this cup might not extend more than 5 centimeters or 10 centimeters. It won't be like a meter long thing that goes on to the back. Whereas for a pipe, if you're seeing just the circle image, we'll have an understanding because we already seen these objects in real life. So they kind of create like an existing neural network that has the spatial understanding that a human has, and based on that, it tries to uh, generate a spatial 3D model of the classes of objects it has been trained on. So there are like airplane models that are there, different sorts of airplane models, chairs, tables, cars, furniture, some basic 3D models that are there for these public data sets. So similarly, like for even like the current state of the art 3D technology is 3D construction technology is being used for the self-driving car aspect, because they have to generate a very less like a model that takes very less latency that can generate the 3D heat map of the surrounding that it's in at that particular time. So it's something similar here, but if you can add another neural network that already has the understanding that if it's seeing a tree, that thing will behave like a tree if we move past it or move from like different perspective views of it. So it's something like that. So as an addition to the project, if we can like get good approximations of axolotl embryos after fixing the angular rotation and axial rotation problems, I think this could be a further way to improve the approximation of the model. So they have like specified different. They try to generate a probability density function for the point cloud that they have based on the class of object that they're dealing with and the additional information that they get based on the data set. They've compared different things here. Multi-view reconstruction again uses ideas similar that were derived from structure from motion. Structure from motion, I think, yeah. Structure from motion, like this was pretty prominent, I think, in the 2000s, as a very accurate way of getting 3D data, and generating like a model based on that. So they have like a very, very big data set of images, and they're trying to generate the point cloud here from all sorts of different perspectives. So I'll just fast forward this till it gets like a proper condition. Yeah, so it's trying to recreate this building here, and yeah, I think this is, so it's very, it depends a lot on how many images are there, and the video feed here also relies on the camera coordinates, if I'm not wrong, because the ISO format they have, they can gauge the shutter speed that is there, the because the aperture also distorts the image either positively or negatively. Like if you're seeing a positive distortion, it's like the front part of the sphere. If you're seeing a negative distortion, it's like an inside part of the sphere, the backside. So it's like it's either curved in a convex way or a concave way. Those sort of distortions are also there in these data sets. So it's still very difficult, just dealing with images and getting proper rendition. So I think if we can actually improve on this and get like a very good general tool for this, I think like at least for the class of ellipsoids, we'll have like a tool that exists for this particular problem.
Yeah. That's great.
And I think if we can get another metric for approximation. Oh, yeah. So yeah. So like if I can get 2-3 metrics for getting the actual approximation data, I think this could also like I could maybe write a paper based on this, because I don't think I couldn't find any regular ellipsoidal structures that were there that have been that somebody has tried tackling this sort of a problem. Even for asteroids and all, like asteroids generating pictures from Earth in image-based data, the data sets that exist deal heavily with, I think, some sort of distance or spatial information that they have, or they assume some things related to that. So yeah.
Yes, there's also a set of assumptions that one makes when one looks at something.
Yeah.
For example, there's a movie circulating right now of a man diving into a pool. Only the pool is empty. There's no water in it.
Okay.
Okay. So the assumption that you're going to have a soft landing can disappear easily.
Yeah.
Okay, so there are assumptions about the material.
The ellipsoid. I didn't get the question.
Oh, in other words, if you're jumping onto a couch, that's fun, but you don't jump onto an airport.
Yeah. Okay.
But you're assuming the couch is not made of concrete.
Yeah. Again. Yeah, because we have like a general idea.
So,
again, that spatial information mapping, inside our own neural network.
Spatial information is not everything.
Yeah. Okay.
Yeah. Well, that's great. Let's keep moving on that. That's pretty good. I'm glad to see that.
In fact, one thing to keep in mind down the road is that embryos are viscoelastic.
Okay.
Yeah. And we had
they can't have a strict 3D.
Yeah, we had a dramatic demonstration of that once. We tried to put an embryo at the top of a small tube.
Okay.
And to keep it there, we put on a negative pressure. And the result was the embryo went right down the tube.
Okay.
It literally part of it literally got sucked into the tube.
Okay.
Okay. So it's worth keeping that.
Another thing I didn't think of. Yeah.
Yeah.
They're not rigid structures.
Yeah, I like to hold the embryos in their own gel, just because it's easier
Yes.
with them. But you can't
It's clear.
it's water. Anyways, yeah, I have to go really soon, so
Okay.
I just wanted to say bye.
Right. Well,
Income tax
yeah,
time.
let's call it a week.
Good work.
All right. Thanks. Good work. Have a
Okay.
good week.